All right, chemistry, let's finish up our video lecture for chapter 5, section 3. So, going through part 2 here. Remind ourselves of what we're trying to accomplish here. Now, remember last time we met, we lectured on the first two trends here, atomic radius and ionization energy. So we still have 3 different trends to deal with, but we're defining atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. We're just simply defining them. Then we're going to compare the periodic trends, right? So that's the period going horizontally left to right. The trends for atomic radius, ionic radius, ionization energy, and electronegativity. But now we're adding this idea of stating the reasons for these variations. So you're going to hear me use terms a lot like effective nuclear charge, shielding, okay, referring to the total amount of negative charge in the electron cloud, referring to the total amount of positive charge in the nucleus. Then define valence electrons, and then state how many valence electrons are present in atoms of any particular main group element. And that one's going to be easy points for you. And then, lastly, we're going to compare the atomic radius, ionization energies, and electronegativities of the D block elements with those from main group elements. So we'll be looking at our periodic and group trends for these 5 different ideas: atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. And we're really going to be looking at the main groups. Okay, we're going to focus specifically on the main groups. And then at the end, we'll start taking a peek at the D block elements. All right, so let's finish off looking at ionic radius, electronegativity, and electron affinity. Just got to get to the appropriate slide. All right, here we go. Electron affinity. Now, in a lot of ways, you can think of electron affinity as the opposite of ionization energy. Let's go back to this idea of ionization energy. It's what we ended last lecture, the first part of this lecture on ionization energy. It was the energy required to remove an electron from an atom. You had to there's some amount of energy change, whether the energy was going into the system or leaving system. There was some energy change, the amount of energy required to remove the atom. Well, if we're removing the atom when we look at ionization energy, when we're looking at electron affinity, we're putting in the system. There's going to be an energy change associated with that addition of an electron, in the same way that there's an energy change associated with the removal of an electron. Okay. Now, we're not going to be doing a whole bunch of thermodynamics right now. So that's a bit down the road. And so we're not really going to get into the significance or the meaning of energy change, the minus sign or the plus sign, and how that refers to direction, not negative or positive values. We're not going to stress that stuff. All I want you to know is the definition of electron affinity and the trend for electron affinity. Okay, and if you really want to master it, be able to give me a reason for that trend. So let's look at the trend. Electron affinity tends to increase, okay, it goes up, okay, the absolute value for that energy change increases as you go across a period. Affinity also tends to decrease as you go down a group from top to bottom. So again, we have a trend as you go across a period and a trend as you go down a group. Now the reason for these trends is as we go across a period, we're increasing the total number of positive charges in the nucleus. Okay, we're increasing the number of positive charges in the nucleus. And so as we increase the number of positive charges in the nucleus, we're also increasing the total number of electrons in the electron cloud around that nucleus. As we go down a group, we are adding shells. We're adding energy levels. Okay, it's kind of like adding layers to an onion. And if we harken back to that idea of atomic radius, as you add a principal quantum layer, principal quantum level, it's like adding a layer to an onion. Each time you add one layer, that onion is getting larger. Just like with an atom, every time you add a principal quantum level, that atom is getting larger. And so as we go down a group, we're getting larger atoms. So that means any atom that would receive an electron, right? Because it's electron affinity, we're adding electrons. That electron is going to be added at a great distance from the nucleus, right? As we go down the group, we're looking at larger atoms, so where they would be added into is further away from the nucleus. The outer edges of that electron cloud is where the electron would be added. So that's further away from the nucleus. Because it's further away from the nucleus, it experiences less nuclear attraction. The effective nuclear charge, right? Effective means it's affecting something. The nuclear charge that affects anything is now less. The absolute, the total amount of nuclear charge is the same, okay, but it's being felt less by that electron because it's further away from the nucleus. Now, there are going to be some weird numbers kind of in the middle of the P block, but we're not going to really stress those because those are basically exceptions to the rules. We're just going to focus on the rules. So let's look at this table of electron affinities. Again, remembering our trends as we go across a group. Let's see. So we got lithium going across to boron. We're dropping down to carbon here over to oxygen. And then we end at fluorine. Okay, so as we go across, starting at lithium, ending at fluorine, notice that the overall value is becoming more and more negative as we go across a period. Okay. Now, this is a tricky one. I'm not going to lie. Electron affinity is probably the most annoying out of all of these. Okay, it's most annoying out of all of these. So if you have questions, please feel free to ask them. PowerPoint's let me down today. Come on, PowerPoint. Here we go. Now we're going to talk about ionic radius. Now the idea is the same as atomic radius, but we're not talking about a neutral atom anymore. We're talking about an atom that has either gained or lost an electron. All right, so we're talking about how large are these things. And we're not going to be comparing positive ions to other positive ions or negative ions to other negative ions. We are going to be comparing the ion to its original neutral state. So let's take a look at a cation, a positively charged ion. A positively charged ion is smaller than the corresponding atom, meaning it's smaller than the neutral form of that atom. So this cation, when it loses however many electrons from its valence shell that it's going to lose, whenever it loses those electrons, it's going to become smaller. Its radius is going to reduce. That's for a cation. For an anion, we're looking at negatively charged ions. We're gaining electrons, and we see that an anion is going to be larger than the corresponding atom, meaning whatever atom is gaining these electrons, once it gains these electrons, it's going to have a larger radius. It's going to be a bigger atom. Now, realize because electrons are so small in terms of their mass, we're not really changing functionally the overall mass. The ion is just as massive as the original element. It's just bigger or smaller. Okay, so it's the difference between volume and mass. We're talking about just overall size, volume. So let's look at what we've done here. This is kind of a summation of the trends that we want to be aware of here. A couple of these we haven't covered yet, but here we see the trend for atomic radius for a group, atomic radius for periods. We have electron affinity for groups. We have for periods. We have electron affinity trend for groups, ionization energy for periods, ionization energy for groups, and then overall metallic character Okay, this is synonymous with electronegativity. Okay, electronegativity. We're going to talk about that in just a minute. Electronegativity. Non-metallic character is the same as being electronegative. Metallic character is the same as being not electronegative. So as you go down and to the left, you get less and less electronegative. As you go up and to the right, you get more and more electronegative. So this is a great chart. This is a great graphic to have out when you're working on your problems, especially when you're working on your quick write. But here is going back to our idea of ion sizes. Notice when you got lithium, it lost 1 electron. Okay, beryllium, it lost 2 electrons. See, it's a +2. It lost 2 electrons. Look how small it got. All right, once it loses those electrons, it gets much and much smaller. And you see this repeated pattern. As you lose electrons, you get smaller and smaller and smaller because there is there's less shielding. There's less electron negative to negative repulsion. They're not fighting each other as much to get into that positively charged nucleus, and they can actually sink in closer to the nucleus. But as we start to add electrons, okay, we're not changing the overall number of protons in the nucleus. We're not changing the total absolute nuclear charge. What we're doing is we're adding more negatively charged electrons that will shield each other from that positive charge. There's more electron negative repulsion than there used to be, but the overall amount of positive charge hasn't changed, and so that forces the electron cloud to spread out more and more and more. As you see, we start with a single charged anion versus a doubly charged anion. That doubly charged anion is definitely going to be larger. Here's a little comic for you. Positive. All right. Electronegativity. Electronegativity is one of the most fundamental ideas that is going to permeate the foreseeable future here. Electronegativity. Electronegativity is the measure of the ability of an atom to attract electrons. The ability of an atom to attract an electron. Okay? You want to get an electron. You want to pull an electron towards you. Right? Towards you. Now, as we explore this idea, keep the octet rule in mind. Atoms want to have a noble gas electron configuration. They want to have a full octet because it results in stability. Right? We want to get that stable configuration. Nature favors low energy configurations. A full octet, a full S and P sublevel, those 8 valence electrons, that is a stable configuration. Nature likes that. So all these atoms want to get that. Electronegativities, they tend to increase across a period. As you go from left to right within a periodic table, within a period, the electronegativities are going to increase. Because as you go to the right, you're actually getting closer and closer to a full octet. For example, let's look at the P block. If we look at oxygen, fluorine, and then neon, we see that neon already has a full octet. It already has a noble gas configuration. It's not going to do anything. It doesn't want to attract any electrons because it already has a full octet. Now, oxygen does want to get some electrons. It needs 2. It needs 2. So it's going to attract 2 electrons. But fluorine only needs 1 more electron, being in group 17, right? Main group 7. It only needs 1 more electron to satisfy its octet rule, and so it's very, very, very close. It's super close to getting its octet full. And so what that means is it's very aggressive going for that last electron. Oxygen is also very aggressive going for its 2 electrons, trying to get its 2 electrons, but not nearly as aggressive as fluorine, just based on the fact that fluorine only has to get 1. Only has to get 1. Oxygen's a little bit further away, so it's not quite as aggressive. Now that was the period trend. Here's the group trend. Electronegativities tend to decrease as you go down a group. Sometimes they remain the same. Sometimes they stay the same, but they're going to decrease as you go down a group. So this is a periodic table that I purposely put in your notes so that you would have access to electronegativity values. I want you to be able to look at these values, and these are arbitrary values based on the Pauling scale. It's a scale that just describes electronegativities. And I want you to notice, especially compared to the table that is titled the summation of periodic trends, look at that metallic character and the non-metallic character arrows. You'll see that arrow that points to a non-metallic character as it goes up and to the right. It matches this general increase, this general bump up in electronegativity values. And you'll see that no atom on the periodic table has a higher electronegativity value than fluorine. And no element on the periodic table has a smaller value than francium. So the single most electronegative element on the periodic table is fluorine. The least electronegative element on the periodic table is francium. Now, there's one caveat I want to throw in here. As you're trying to follow this trend for electronegativity, as you go up and to the right, it increases. Do not continue up into the noble gases that would be in group 18. They have no electronegativities. Remember, they already have a full octet. They don't want to gain electrons, so they don't. Electronegativity is the ability of an atom to gain an electron, to attract an electron, the extent to which it attracts electrons. If you're an atom that already has a full octet, you're not going to attract anything. So this trend for electronegativity stops at group 17. It stops at the halogens. So just be aware of that as we try to problem solve with this information. So what have we done so far? We have defined atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. We've tried to compare the periodic trends for atomic radius, ionization energy, electronegativity, and we've tried to state the reasons that they are that way. We've defined valence electrons, and we can state how many valence electrons a particular main group element has. And we've compared the atomic radius, ionization energies, and electronegativities of the D block elements with those of the main group elements. All right, guys, I will see you next period.